Now we have the same sort of consumption problem, where we have to integrate a rate, or net change rather, but now we have more of a tabular data. And, in recent years, 10, 20 years or so, there has been a lot more emphasis on this, like, tabular data question, okay? So, a pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. Okay, makes sense. The rate, gallons per minute, so they'll either tell you specifically the rate, or they will tell you some information, some other words, and then you have something, the units, gallons per minute. So either way, you should be, like, the antenna should just go up and say, okay, rate. The rate at which the pump operates is recorded at 10-minute intervals for 1 hour, as shown in the table below. How many gallons were pumped during that hour? How many gallons were pumped during that hour? So we have the rate, and now what we want is the net amount, the total amount. All right? So again, we're given the rate, just like in the other problems. You're given the rate, you need total amount. Okay? Mathematically, the word for that is net change. It's the exact same thing as what we did here with the potato consumption. We were given a rate. We wanted the total amount. Okay. How did we find it? Well, we identified that it's the area, right? And when you're given an equation, how do you find the area under the curve? You integrate. But when you're given this, you can still find the area under the curve. We have lots in our disposal, LRAM, MRAM, and so on, and then trapezoidal rule. In parentheses here, it says use the trapezoidal rule to approximate. You may be given that, you may not be given that. You can really choose either. I have to say the trapezoidal tends to be the most accurate, and it's the most usual, most conventional way to do it. So T is going to be 1/2, right? And then these are the heights, right? And you see they're equal intervals. So it's going to be 10/2 times 58 plus 2 times 65, 58, 55, 59, 60, 1 of 63, and that is a total of 3,575 gallons. Okay? Is it gallons? All of these have a unit of gallons per minute. So all of these have a unit of gallons per minute. And then to the left, I have 10/2. The 1/2 is just from the formula. But the 10 has a unit of minutes. So what I've done here is I've multiplied a quantity with a unit of minutes with one with gallons per minute, and that leaves me gallons. Okay? Okay. So we're going to take this idea and we're going to expand it to 7.2. Areas in the plane. We're going to talk about area between curves. Okay, this is it. This is like the biggest thing in calculus. This is why we do calculus. All right, so suppose you have two functions, f of x and g of x, and take a look at what it says here. It says here f of x is greater than or equal to g of x throughout a, b. What does it mean that f of x is greater than g of x? That means f of x just sits higher than g of x, okay? Sits higher or above g of x. That's what it means when something is greater than another function. Okay, so if f of x is greater than g of x throughout AB, then if we need to find the area between the curves from A to B, right, we have to find the integral, the difference of the integrals. Well, let's see if that's true. All right, so suppose this is f of x. How would I find the area under that curve? Take the integral, right? So that area is the integral f of x dx from a to b. Okay? Now, suppose I had another function. Suppose I had another function, g of x. How would I find the area underneath g of x? Well, that's the integral g of x dx from a to b. Now, if I had to find this area in between them, what would I do? I would take the black integral, which goes from the black curve to the x-axis, minus the red integral, which is that red portion, and that gives me the purple. Is that right? So the purple region is the black integral minus the red. Okay? All right, in short, what we do is, when we're integrating integral f of x dx minus integral, oh, this is g of x. I'm so sorry. This is g of x. Okay? When you have integral of f minus integral of g, we can simply write it together as integral of f of x minus g of x dx. Okay? It has to be so that the bigger one is first, then the smaller one. So the way we do it is the area between the curves is equal to the integral from a to b, okay? The upper minus the lower dx, okay? That's the area in between. All right, so let's do one example here. All right, let's do one example here. I have to find the area between y equals negative x squared plus 6 and y equals x from x equals negative 3 to 2. All right, so here, let's see where negative 3 and 2 are. X equals negative 3 is here. That's where these curves first intersect. And then 2 is here. That's when they intersect. So what I need to find is this area in between. Okay? So now.
So would you find the
okay, so here's what we're going to do. We're going to say area is the integral. And if we're going from negative 3 to 2, then that goes here, negative 3 to 2. The upper curve, okay, literally the one that sits above, is negative x squared plus 6 minus the lower one is x dx. Okay? Yeah.
Is it are you just trying to just do the integral from negative 3 to 2 negative x squared plus 6 dx, and then the integral from negative 3 to 2?
It's the same thing, except this is quicker. Yeah.
How come we're looking for the part that's up top and not like the part that's like below it? Like how when the line intersects it?
Because it says find the area of the region between the two curves. The region between the two curves is this, from negative 3 to 2. The region that's enclosed by the curves is this one. Right? You have the parabola and the line. So between the red and the blue, it's that line. Yeah. Yes and no. It could be like, it could have been like from 0, you know? Like it could have been from x equals 0 to 2. In that case, you just cut it here. Huh? No, what I'm saying is it doesn't have to go from the intersection to the intersection. You know? Or it could be from like -1 to 1. Yeah.
What if my mom was a sine and it was like above and below?
Okay, we're going to do like 50,000 examples and hopefully we'll hit every single one. Okay, so here, most of the time you'll be asked to, you'll be able to put it in the calculator, and so we will get 20.833. Okay? Cool. Okay. Next. Okay. Find the area of the region between y equals secant squared x and sine x from x equals 0 to x equals pi over 4. All right, again, identify which one is on top, which one is on the bottom. The top is the higher function, it's the greater function. So we're going to integrate, all right, to find the area from 0 to pi over 4. Make sure you label this as area equals. Here, it's going to be secant squared x minus sine x dx. All right, and you know what? Just for the sake of practice, I want to do this by hand. So here, this is going to be, the integral of secant squared is tangent plus cosine from 0 to pi over 4. Okay, when I plug pi over 4 in here, tangent of pi over 4 is 1 plus root 2 over 2 minus tangent of 0 is 0 plus 1. So this will be root 2 over 2. Okay. Notice the form. Okay. What is this? Area. A equals, cute little integral. Okay. And then I have, the next step is clearly, is there any discrepancy, any ambiguity, any question, all right, about what the step that comes after this? Is there any ambiguity over where my second step is after this? You know exactly where it is. It's here. You can follow it. Do you know 100% what the next step after that is? Yep. Do you know what comes after that? Yep. So this is it. We are not, don't leave a scavenger hunt for the person grading your test, right? Because nobody has time for that, okay? So this is what I want, or I will not grade, okay? Clear progression. You want to do it horizontally? Do it horizontally. That's totally cool. But there should not be, it should not be going in 50,000 directions. All right, let's move on. Find the area of the region enclosed by the parabola y equals 2 minus x squared and the line y equals negative x. Okay, we're going to draw these. Y equals 2 minus x squared, you need to be able to draw it like this. Okay, so that's a parabola that faces down. It goes up here. You should also be able to, more or less know where it hits the x-axis. So, in this case, right, when y is equal to 0, x is plus or minus root 2. How much is root 2 these days? 1 point, it's somewhere between 1 and 2, right? So this should cross the x-axis here, and it crosses the x-axis here. Now, I need to draw y equals negative x, but I need to get the intersection points correctly. So let's figure out, where do they intersect? Okay? So first, find the limits of integration by solving this equation. You need to figure out where the two of them intersect. And so you say, okay, 2 minus x squared equals negative x. And then when we solve this, 0 is equal to x squared minus x plus 2, x minus 2, x plus 1, So 0 is equal to negative 1 and 2. Oh, I'm sorry, x is equal to negative 1 and 2. So at negative 1, and at 2, these two intersect. Okay, when x is 2, what's y? For any of these, when x is 2, okay, so look. When x is 2, what's y for this one? Negative 2. So at 2 and negative 2, these things are going to cross. So you need to draw it so that they do both hit those points. Okay?
I mean, like, after when you just draw it,
Yeah, but you should know. Yeah, but you should know, and you need to do it precisely. So now look, because at these points of intersection, so because at negative 1, the y values for both of them are the same, when you want to find the y value of the intersection, you can plug negative 1 into either equation, because at that point they will have the same y value. All right? So now, I know that y equals negative x is the lower curve, and y equals 2 minus x squared is the upper curve. So when I integrate, I know that I'm going to go from negative 1 to 2. And it's going to be 2 minus x squared minus negative x, so plus x dx. And that's equal to the area. And so now the area, when all is said and done, is 9 over 2. Okay, now, I know somebody's going to ask me, how do you need to know those y values? And you do, because sometimes you have to go vertically instead of horizontally. So it's important that you do, okay? All right, so that's that one. All right, let's do one more. All right, from the area of the region between the graphs, y equals 2 cosine x and x squared minus 1 using a graphing calculator. Okay, so here we go. You've got 2 here, right? Just by looking at this, which one is which? What's this top one here?
That's the cosine y two cosine x.
That's 2 cosine x, right? Uh-huh. And then this one is y equals x squared minus 1. So I know which one is the higher and which one is the lower. Okay? All right, so here's what we're going to do now. The area is going to be 2 cosine x minus x squared minus 1 dx. Okay. It doesn't matter because we're going to plug it into the calculator. So why don't we go ahead and plug this into the calculator? Go ahead and take out your calculators. So we're going to have 2 cosine x and then another one we're going to graph is x squared minus 1. All right, and look at the window. It goes from negative 3 to 3 and negative 2 to 3. So what I want to do first is go to menu, window, and I want to do a trig zoom first. Then I want to go to menu again. It calibrates the axis so that it goes like by pi over 2, pi over 4. Yeah. And then look at what we're going to do now. Go back to window settings. Let's get this cute window, that they have here. So let's go from negative 3 to 3. And then here negative 2 to 3. Okay, that's a window zoom trig. Okay, now I need to find the points of intersection. So, menu, analyze graph, 0, And, okay, so it says, no, sorry, I didn't want 0. I'm sorry. I wanted the intersection. So menu, analyze graph, intersection. Here, lower bound, upper bound. And then let's do it again. Menu, analyze graph, intersection, lower bound, upper bound. And I just want to move that other text here. All right? So, okay. So these are the points of intersection. Now, I have a problem here. The problem I have is, again, I have that float issue, right? I just downloaded a new version. That's the reason. So get rid of this. You should have at least 3 decimal places here. So for that, we're going to go to Menu, Settings, and here you see how it says float. Just make it float, okay, without the number. And so do you see how you now have the number in their, full glory? Okay. And now, okay, go here. We're going to, so hover on the X coordinate of the intersection. You're going to right click. And again, on your calculator, the right click is Control and Menu. So while you're hovering, Control Menu, and you're going to want to store. If you did A for 1, do B for this. This is for you. Press Enter. Okay? Now, go back. Here. Menu. Oh, no, sorry. Here. Menu. Calculus. Numerical integral. Type in A. All right? And type in B. That's crazy.
What?
Yup.
What?
And then type in 2 cosine X.
Oh, you asked one. I mean, right? That's one of them.
You can do that too. I'll do that later. Minus X squared minus 1. Dx. Enter.
Oh my god.
But that's not the right answer.
No, 6.2. Yeah, your parentheses.
Oh, silly.
Nine.
4.995. Okay?
Wait, I didn't get that.
I got that, and that's what
Oh,
counts.
oh, I'm
Okay. So let's go back here. Okay, a few housekeeping stuff now. Our points were symmetric, correct? So you have to do this. Let A equal 1.265. That was the point of intersection, correct? From here, 1.265. Okay? And then, now, because they're symmetric, you don't really, technically we didn't have to do A and B. I showed you that in order for you to know how to do it. But technically, you could have also done negative A to A and done the whole thing. Okay? Dx. Now, there is another beautiful thing with this. Do you see how this is symmetric? So you could have also done area equals 2 times the integral from 0 to A, 2 cosine x minus x squared minus 1 dx. And both ways, we get 4.995. Okay? This is the beauty of the features of the calculator for which we paid all this money. Sometimes there is a very clear benefit, and you'll see, like, especially like if it's a mad integral that you have to do by hand, It just minimizes the work because one of it is 0. You know what I mean?
Right.
Like when you plug it in. Okay, so when you go here, when you go here, you could also have done menu, numerical integral. So you could have also done negative a to a. Okay, and you could have also done, because we've already stored our functions, you don't have to retype your functions. You could just do f1 of x, okay,
So that's
minus
the equation.
f2 of x.
How long can I save this variable?
Until you die, until you change them.
So wait, so
Okay, so,
You could just go clear it.
oh, was it?
this way,
Did I plug them in the wrong one? Yeah.
if I
Oh, because my A is, oh, sorry. My A, you know how I define my A to be the right one? The
Yeah.
negative one? That's why I got the negative answer here, right? If my A had been defined as the positive one, I would have gotten, so I'm doing this flip. This is the negative. I did, yeah, because I'm going from the negative value, or the positive value to the negative value. Okay, somebody was trying to ask a question. Yeah.
so for this method using variables to store the numbers, will that only work on that one? So you pulled the scratch pad on the graph slide. So if you were to exit the graph, would your A still equal 2 points?
Yeah, as long as you haven't redefined
So
it,
we have to. So the thing is, just keep redefining.
you have to redefine it. Plus, like when you put in a new document, or when you put in a new graph and you get a new intersection, you're going to have to now call that point A. So it'll
Yeah,
like
so you just
overwrite.
disable it,
Yeah. Okay. So, don't quote me on that. Let's try it. I'm also new to the TI Inspire. So, now, I had a question earlier about what if the boundaries change halfway, right? And so here we go. What if you have a boundary with changing functions? Hey. Thank you. So here, if a boundary is defined by more than one function, we have to partition it and do 2 separate integrals with the 2 separate boundaries. So, for example, look at this one here. It says find the area of the region R. Okay, let's talk about that for a minute. This is common. Every single time, the region of which you need to find the area is always given the name capital R. Region R, okay? So, you need to find the area of the region R in the first quadrant that is bounded, okay, above by y equals root x. So above by y equals root x. Okay? And below by the x-axis and the line y equals x minus 2. So this is the region here, right? So above the whole time, it's the blue y equals root x. But on the bottom, you have 2 regions. In the first case, look at, until here, below the bottom of the region is what? What is this? That's the x-axis, which is y equals how much? 0. And then to the right of that boundary line, I have y equals, what was it? X minus. Okay, so what I'm going to do is first, this integral, that's going to be the first integral, so let's write that down. So area is, okay, this integral spans from x equals 0 to x equals 2. So I go from x equals 0 to x equals 2. I'm ignoring everything past that purple curtain, okay? On top, I have y equals root x. Minus, on the bottom I have 0. Obviously you don't have to write the 0, we'll do it this one time. Plus.
Why are we splitting it?
Because there is no other, because if you do root x minus what?
Well, isn't it the function x?
Yeah, but starting here, right? If you're in this region, what's above you? So suppose you're sitting here, or you're standing here. What's above you? Root x. What's below you? 0. Here, what's above you? Root x. What's below you? X minus 2.
Do they count the boundaries of the x-axis? That's why I'm confused. They're only looking for boundaries of the function, so why would they even be counted as one that's created by the curves? That makes sense. So we're trying to find areas in between the curves. So
Right.
why would that even be an area under the curve if it's not?
Oh no, but it says here, bounded below by the x-axis and the line. So
they're specifying.
Mhm.
that.
right. So the region, it's a finite region. Otherwise, this goes down until infinity, and that's
So they're
infinite.
saying that. Okay.
Yeah, it's this shape. Yes.
Can you split it up into from 0 to 4 of the first function and then minus from 2 to 4 of the other one?
No.
Because
For the second one? No. So for the second one, here's how it's going to work. The second function, the second partition here, starts at x equals 0 and goes to x equals 4. I'm sorry, x equals 2 to 4. So now on top I have root x, on the bottom x minus 2 dx. Okay? And that's how I define my partition. So it's literally like two completely separate regions. You're doing it separately and then you're adding. It's like when you were in algebra or geometry and you had, those like, yeah.
The area of one minus the area of the other.
No, the intervals, it's the area of this purple, the purple area plus the red area. The purple area goes from 0 to 2. The red area goes from 2 to 4.
Wait,
Why can't you go from 0 to 4 with one of the lines and then subtract the other one, the area under the other one?
But the other, but this doesn't exist from 2 to 4. I mean, from 0 to 2.
I'm saying split up the equations into their own parts. Like one of them is from 0 to 4 of just root x, and the other one is minus from 4 to 2.
0 to 4 of root x finds all of this.
Yeah, and then minus another one of, from 4 to 2 of the other.
Okay, but 4 to 2 of the other, 4 to 2 of this red curve, 4 to 2 of the red curve is this region. It's the area underneath.
Wait, I'm just finding the area of that region now because it just keeps.
Yeah, you just do the thing with,
Okay, let's figure this one out. It's 3.333. Okay? And then let's move on and then we'll come back to this. Okay?
Would you even just account?
Okay, so look at this function here, right? Look at this function here. If we were to integrate like we were before, so let me highlight these in different colors. So I have a blue function here. This is x equals f of y. So I have that blue function there. And then here I have a red function. Okay? So if I went top to bottom like that, all right? If I was here, look at this. I have red on top, red on the bottom. Here it's a different story. And then here I have blue on top, blue on the bottom, right? So like boundaries are shifting, right? Functions are shifting. However, if instead of doing that, if I looked at a region like this, okay? If I looked at a region like this, what are the boundaries of this region now? I have a left and a right boundary. The left is the red one, the blue is the right one, right? And if I'm here, left is red, right is blue. Here, left is red, right is blue. So if I look at my function horizontally now, I have the same boundaries to the left as I have to the right. So what I can do in this case is solve my equations for x in terms of y, and now I integrate, okay? I integrate f of y. So solving my equations for y, I integrate over the y values. Instead of going a to b horizontally, I now go c to d vertically. All right? And so what I need to do in this case is I have to change my equations so that it's x equals instead of y equals. All right? So if I had, so for example, if you have y equals, I don't know, the square root of x, I solve that for x, and I say y squared equals x, right? And so x equals y squared, that's what I integrate. All right, and I go from a y value to a y value. All right, so let's take a look at it. Let's take a look at that same example that we just did, this same controversial example. All right, let's do it again now. All right, we're going to integrate that same function, but now, okay, so I still want to find this region R. Okay, now what I do is if I look at this horizontal line, to the left, I have y equals root x. To the right, I have y equals x minus 2. And for the entirety of that region, it's the same. Okay? And so what I do now is I solve the blue one. I say x equals y squared. And I solve the red one. I say x equals y plus 2. Okay? And so now what I'm going to do is I'm going to integrate this with one thought. Okay, so now, if the higher function was the one on top before, now the higher function is the one to the right. Okay? So now I need to integrate right minus left. Okay, so the function to the right is y plus 2 minus the function to the left is y squared. All right? And how long does this whole thing last? It goes from 0 to 2. Okay? But now I need to integrate with respect to y, so it's dy. And so if this is the area, when you plug it in, sure enough, it's 3.333. Okay? All right? So it minimizes that, so there is no need now to even split it up. And so you're usually going to be tasked with, okay, so here's a region, find the area. And so you have to choose, wait, is it easier to integrate with respect to x, or is it easier to integrate with respect to y? Sometimes if you do it with respect to y, you get away with one integral. But with respect to x, you need 2 or 3 sometimes. Okay? All right, let's take a look at this one. All right, so look at this. Find the area enclosed by the graphs x cubed and y squared minus 2. So the region I want is this. And again, if you were to go with respect to x, right, on top and bottom here to the left you have different graphs, different boundaries, and then here you have different boundaries. So you would have to do separate integrals. However, if we went with respect to y, right, the whole time from y equals -1 to this top intersection point, I only have one boundary to the left, one boundary to the right. So that's what we're going to do. That's how we're going to do it. Okay, so I have here y equals x cubed, which is this one. But I'm going to solve it for y, I'm sorry, solve it for x, so I'm going to get that x is equal to y to the 1 over 3. For this one, I already have x equals y squared minus 2. So let's integrate. Alright? Area is going to be which goes first? Which function goes first? Blue or red? Blue, because it's to the right. Where are the positive x's? Where are the positive x's? Here. So if it's x equals something, the positive x's are to the right. It means those are where the higher functions are going to lie. Right? So it's right minus left. So it's going to be x equals y to the 1/3 minus y squared minus 2 dy. Okay, now my lower bound is -1. Alright? Well, what about the upper bound? That we're going to do with the calculator. So let's go to the calculator. And so let me clear these and we will graph the other one. So what do we have here? We have y equals x cubed. Right? And then F2. Huh?
It's still in tray.
It's okay. Let me find my functions first. So here, how am I going to put this second one in? It's x equals y squared minus 2, right? So it's y equals the square root x plus 2. Why can't I do square root? It is, I'm only going to do the top because I just want the intersection on the top, right? But it is. So the square root of x plus 2 we said? Here. Alright, so let's find the point of intersection here. So menu, analyze graph, intersection here. Okay, now I'm going with respect to y. Sorry. I'm going to integrate with respect to y, correct? So I go to the y value, right click, store. Let's do C this time. Because control and menu. Enter. Alright? So here we go, 1.793. So here I'm going to say let C equals 1.793. And so here you can go from -1 to C. You either do it this way, or you go and you physically write in 1.713 on the top of the integral. But you can't do -1 to C when you haven't defined what C is. And now I'm just going to go and integrate this in the calculator. So I'm going to do menu, calculus, numerical integral. And so we're going to go from, what is it, -1 to C? And you put in your y's this time, but in terms of x's, right? So it really doesn't matter. You could do them in terms of y's as well. So you could do y to the power of 1 over 3, or you could do x to the power of 1 over 3. It really doesn't matter. Integration is integration. So minus x squared plus 2. But then here you have dx. The calculator doesn't know the difference. And so it's 4.215. Okay, now the homework from this is from the book, all right? And it's on the sheet that I gave you. My advice to you is to go home and to do it tonight, even if it is due Thursday, because by tomorrow, like 30% of it will leave. It's like an exponential decay, right? 30% will leave, and then 70% will leave, and it'll all be gone. Okay? So now